Very warm welcome to all of you in this HW2022 rollout session for NVHD and C. Today, myself and my colleague Uma Mahesh will be covering the topics as listed on this slide. 2022 is going to be a big release for NVHD with some significant new features and enhancements. Now we can say that we are truly on a journey to cover complete frequency range of analysis with the introduction of SEAM and some very advanced topics like aeroacoustics. So let's start with the topic of optimization and correlation to improve the correlation. We all know that NVHD has very advanced and competitive features to study and analyze correlation for mode shapes in terms of MAC and NVH responses in terms of FRAC. So this slide just talks about some basics on MAC, which stands for Model Assurance Criteria. MAC basically determines the degree of similarity or correlation between two sets of model results. So it tells you how close the two mode shapes are, how closely they are matching with each other. So if you see like this top animation is coming from test and this bottom animation is coming from simulation results. So these are two mode shapes, one from test and second is from simulation. This middle image is shows the MAC between test modes and simulation modes on a scale of 0 to 1. So the x-axis shows the mode shapes and corresponding frequencies coming from test, and y-axis is for simulation mode shapes and frequencies. Typically, the MAC value more than 0.7 is considered as a good MAC or good correlation, meaning the mode shape between test and simulations are very closely matching. And as the value of MAC goes less, so if it is, let us say 0.4 or 0.3, it means the mode shapes are not matching closely and it's a poor correlation. So this is how the MAC tells you about the correlation, how the mode shapes are matching closely or not. So application wise, MAC is used for all CA and test correlation activities across industries. It is used in four-wheeler, two-wheeler, in heavy machinery, aerospace, shipping, everywhere. It can be considered as an industry standard to evaluate correlation. On this slide, this image, the bottom image, it shows a typical MAC plot with poor correlation, in which you will see that some of the MAC values are very less than 0.7, and there is also a frequency mismatch. So this kind of MAC plot indicates a poor correlation between test and CA results. And this MAC plot indicates good correlation between test and CA results, where the MAC values, most of the MAC values are more than 0.7 and there is no frequency mismatch. It's kind of a diagonal one. So this is considered as a good correlation. But going from this poor correlation to good correlation is not a one-time activity. It evolves over a period of time. It needs a lot of systematic efforts to improve the correlation. So the point is, NVH analysts do spend a good amount of time and some systematic efforts in taking their correlation from poor to good. And this is what we are going to talk in next few slides. So we did saw a slide or the image of poor correlation. So let's speak some more time about it. So I did say that if the MAC values are less than 0.7, then it is considered as poor correlation, and also there are some frequency mismatches here. So why this poor correlation may come? So it can be because of test. It can be because of simulations too. So it is not always that test is always right and simulation, there are problems in simulations only. So in case of test, it may be a result of incorrect sensor location. So sensors are not placed properly. The users don't have sufficient sensors, and both these can result in a situation where the mode shape itself is not captured properly. One more reason can be improper excitation location, in which your shaker or your hammers are exciting the structure at such places that it is not able to excite the complete structure. So these are the potential causes for mode shapes not being captured correctly. In case of simulations, it may be because of incorrect modeling practices, thickness mismatch between your test prototype and simulation data, mismatch in the material properties between simulation and test, and there can be some modeling mistakes too. So the test results can be improved by updating your test setup or improving the test setup, and simulation results can be improved by updating the FE model or the modeling practices, or correcting some of the modeling issues. So there is a possibility to do the correction on test side as well as on the simulation side. Now, in this new optimization workflow, which we have introduced for Mac, we are basically focusing on updating the FE model to improve the correlation. So in this Mac utility, a new tab is introduced called as optimization. And in this, the user will be able to select and define design variables, specify the objectives to maximize the MAC value for those modes which have lower MAC values, specify the constraints to maintain the MAC, or also to specify the constraints to maintain some frequency values. And once the optimization is complete, then in the display tab, user will be able to see the MAC comparison between baseline and optimized, and also compare the design variables, how they have changed from baseline to optimized. So this is a seamless workflow which allows users to set up the optimization process, run it, and finally view the optimization results. So this is, let's look at the implementation. This video will show you. So the first step which starts with is to calculate the MAC for your test and simulation results. So once the MAC results are calculated, you can go to the optimization tab. And in here, you first load the FE model associated with your simulation results. Once the FE model is loaded, then in the design variables tab, you can define your design variables. Currently, you can select design variables as gauges or material properties. Here, I'm selecting some properties by selecting it from the screen. There is also a possibility to select all the properties from the advanced selector. So it is a typical guide bar, which you will see in the Unity framework. You can select your attributes. I am selecting now thickness and specifying my lower and upper bound. I'm selecting 10 plus minus 10% variation for thickness. And now I'm selecting materials as design variables. Here also select the attributes which are needed. Once the design variables are selected, you can review them, and here I have applied them. The next step is to set the objectives. So I'm looking for the mode shapes where MAC value is less than 0.7. I have selected those. Those are listed here, and I have said that maximize those. Then the next step is to set the constraints. So these are the modes where the MAC value is more, and I want to maintain the MAC value for these modes. I don't want to deteriorate them. And at the same time, I want to basically set some constraints for the frequency. So I want to remove this mismatch. So what I'm saying is the mode 12 frequency should be maintained between somewhere between 150 and 170 hertz, so that this mismatch is taken care. And I can also specify the constraint MAC. I can specify the number of runs too. And here I'm specifying 300 number, I think, yeah, 200 number of runs. And once I click evaluate, it goes to the job manager and starts running the optimization runs. Once the optimization is complete, you can see the comparison between the optimized MAC and the base MAC. Here you can see that the MAC value has increased from, this is baseline on the right hand side, left hand side is optimized. You can see that the MAC values has increased from 0.7 to 0.76. 0.66 to 0.8, 0.48 to 0.67. So there is a lot of improvement in the Mac. You can also review the design variables, basically showing you how it has changed from your nominal value to optimized value. So this is the overall workflow for Mac optimization. It is very, very efficient and streamlined workflow, which allows users to update their FE model, improve their Mac, and finally, the end result is helping users to update their modeling practices. So in general, it's valid for test CAE combination results. The users need to plot it, select the mode pairs with poor Mac, select the design variables from the FE model, specify the constraints and objectives, run the optimization, and optimize the design variables from the FE model to improve correlation. So this is the in general workflow for Mac optimization. Now next, let's go to the next topic, and that is flexible RIM handling in CD tire. This image shows a typical scenario nowadays where you have a same car, but coming up with different rims. You can have a baseline rim, sporty rim, luxury rim. So as the car it goes, the rims may change with the version of the car, the same car, but in the different variants. So these different rims, they affect vehicle NVH performance? Yes, definitely yes, and majorly road NVH, because we know that the road excitations will go from road, then they will basically the rim dynamics will play a role here. This slide just shows the different FRF curves coming from different rims. So here, this is a test setup in which user is trying to acquire different FRF responses for different rim designs. And here you can see that the rim dynamics differs based on the rim design and construction. And this in the end affects the road NVH performance, because as the rim design changes, the dynamics change, and eventually it will change your NVH performance. So in last few webinars, we had seen that NVHD has a complete, seamless and integrated process for handling various tires necessary for NVH simulation. So we have CD tire front runner, traditional DMIGs supporting symmetric and asymmetric matrices, as well as traditional model of tires. But all of them were from rigid rim. Now, what we have introduced is in CD tire, the user will be able to consider the flexible rim. So the flexible rim effects can be easily get captured. So this is the new implementation for CD tire. Let's look at some highlights. So now for tires handling, there is a new flag which specifies whether a particular module is for a tire. For a module which is flagged with tire module, there are two at a high level. There are two representation types for tire module. One is model, and second is DMIG. And the DMIG can come in ASCII files as well as in CD tire. And below, inside CD tire, you have two options of rigid rim and flexible rim. Once a user sets the option of DMIG, CD tire, and flexible rim, he is able to read in different FE models corresponding to different rims. So here you can see there are three rims: baseline, luxury, and sporty rims. So user will be able to read in all those three FE models of the rims. The user will be able to create the CD tire for each of the rim. And each module representation will be an exclusive combination of a flexible rim and a CD tire. So user can pick and choose and make the combinations of flexible rims and tires. So let's look at the quick video for the implementation. Here I have created a module and specifying the tire module flag. Once the tire module flag is set, then the user can specify what representation type. I'm going to CD tire flexible rim, specify the label for it. And here the user will read in the FE model of the flexible rim. Once the rim is ready, it can be positioned. And the next step is to create the tire. Read in your parameter file, create the CD tire, and then apply it. And this will create a combination of flexible rim and tire. So now this one module is a combination of this flexible rim and tire, and the connection between tire and rim is automatically created in terms of RB3s. I can use this tire rim combination and position it on the rear left side, so that I don't need to read in the, it's not necessary for me to repeat the whole process. So here what is going to happen is the flexible rim, which is already created, is available for selection. The only thing I need to do is change the label. So I'm going to read the rim. The tire associated with is already populated. What I need to do is I need to position it. In this case, what is going to happen is we are going to write out a transient include for the rim, and the tire will be positioned accordingly. So you see, like, the same rim and the same tire is positioned on the rear left side, but the tire will be taken care by deeming mode, and the transient include for flexible rim is created. In the same way, users can also create the symmetry of the rim and the tire combination, so that this left hand side gets reflected to right hand side, and you don't need to necessarily go through the complete process of reading the rim and creating the tire. So this is the overall process for handling the flexible rim. These are just some results showing how these rim affect the NVH responses. So 3 type of rims. We had one base rim, then we had one luxury rim, and we had one sport rim. For these 3 different type of rims, we put them on the full vehicle model and generated some NVH responses. So you can see, like, the change in the NVH response. It's very significant, and this is basically a very powerful feature to handle the flexible rims in the tires and study the effect of rim dynamics on vehicle responses. And it's not only about rim dynamics, but you can keep the same rim and change your tires and also see the effect on the vehicle responses. So there are some very nice features in here. You can automatically identify the ID ranges of the FE model of flexible rim. There are options to position the rim and tire. There is automatic creation of connection between rims and tires. It is possible to have a symmetry for rim plus CD tire and also position the rim and tire. Okay, so let's move on to the next point, and that is engine mounts optimization. There are some enhancements in here. During the last webinar, we had seen some enhancements in 2021.2 timeframe for engine mounts. And these are the next set of enhancements. And here, the idea is to support the nonlinear stiffness of the mounts, which you can get in terms of force versus displacement, or you can also get in terms of stiffness versus frequency. And for this nonlinear stiffness of the mounts, it is possible to calculate the mount displacements and reaction forces for various static and dynamic loading conditions. So this is one very important enhancement, or a very big enhancement. And for the optimization, we have introduced equation-based constraints for mount stiffnesses, wherein the user wants to maintain some relationship between the stiffnesses in various directions. In some cases, users want to maintain the stiffness in X and Y directions, or they want to maintain the stiffness with some equations, right? Like, for example, the stiffness in Z direction should be more than or equal to 2 times the stiffness in X direction. So such kind of equation-based constraints user are interested in. So let's look at the implementation. So in the mount optimization utility, you will see that now there are options to specify a static stiffness, or frequency versus stiffness, or displacement versus force stiffness. So these 2 options, frequency versus stiffness and displacement versus force, they are specifically for nonlinear mount stiffness. So if a user chooses frequency versus stiffness, then he can read in this option from coming from the CSV file or a text file. And he can also review what kind of nonlinear behavior that stiffness has. So user can go and read in the nonlinear stiffness values for the mounts. I have just read in for all of them in X, Y, and Z direction for all three different mounts. And for this nonlinear stiffness, I can basically apply and calculate the rigid body mode frequencies and kinetic energy distribution. For those, I can calculate mount displacement and reaction forces for various static conditions like braking, cornering, vertical, max torque. It is also possible to add the custom static load conditions as per user choice. And here you can see that here these are Z direction displacement. You can have displacements as well as reaction forces. So this is for static loading condition. Now you can also do this displacement and reaction forces for transient loading conditions. So here it is. You can see that this is the torque versus time. This is applied at the power tensor center of gravity. And for this transient loading condition, we can calculate the mount reaction forces and also the displacements. And this is supported for now. You can see that it is supported for the nonlinear stiffness of the mounts. Once that is done, then in the study tab, in the deterministic optimization, in the study tab, there are three options. One is sensitivity, deterministic optimization, and RPDO. Now let's look at the new constraints which are introduced for deterministic optimization. So in the deterministic optimization you can define design variables, objectives, constraints, and also the display. So for constraints, there are some standard constraints for frequency and some advanced constraints. So here, what I'm trying to do is I'm trying to say that how should be my frequency values be maintained for vertical mode and the bounce mode. And in the advanced constraint, there are options to specify the constraints for the stiffnesses. So here what I'm saying is the stiffness in Y direction for mount 1 should be equal to stiffness in Z direction. So such kind of advanced constraints the user can specify, like multiple advanced constraints. So here for mount 1, the stiffness in KY and KZ should be maintained same. Even after optimization for mount 2, the stiffness should be maintained for KX direction with mount 3 KX stiffness. And for mount 3 KZ, its stiffness value should be more than KX direction stiffness, but by twice the amount. So it is like KZ stiffness for mount 3 should be 2 times more than KX stiffness. So such kind of equation-based constraints can be introduced now. And once user can submit the deterministic optimization run. And now here you can see after the optimization, this is basically baseline MAC. This is optimized MAC. So you can see that now the rigid body mode frequencies are properly decoupled. There is no coupling with this kinetic energy distribution plot shows that there is no decoupling. And now when you go to the review, you can oops. you can see that after optimization, all the constraints are satisfied. We had said that the stiffness in ky direction should be maintained as kz, so this is satisfied. We did say that kx for mount 2 and mount 3 should be maintained. This is satisfied. We did say that kz should be more than twice the value of kx, so even this is satisfied. So all the constraints are satisfied, and all the objectives are met. So this is what has been implemented in engine mounts optimization. So nonlinear stiffness of the mounts, as well as equation-based constraints for the stiffnesses. So now engine mount optimization utility is kind of has become very powerful, and it's an end-to-end solution for powertrain mounts optimization, which can cover rigid body modes, modal decoupling, kinetic energy distribution, static loading conditions, dynamic loading conditions, torque roll axis, direction and decoupling, sensitivity simulations, as well as optimization of the powertrain mount layout. So it is very much complete. The next few slides are about newly introduced signal processing functionality in 2022 to process the CA results. In the NVH post utilities, a new option is introduced named as general signal processing, and this is to process the flow results coming from CFD calculations. This advanced functionality has been developed by integrating UFX, Hyperview, Hypergraph, and Compose. So it is basically meant to handle the results coming out of UFX and post process it using Compose and visualizing it using Hyperview and Hypergraph. Most of these flow results are typically in time domain, and they are intensive in terms of the data content. They have a huge data content, and this functionality allows users to review this data in time domain, post process it, and then review the data in frequency domain, in narrow band as well as in broadband, and do all kind of signal processing on this data, and do some meaningful analysis out of it. So there are some key capabilities. It allows users to do transient flow data reviewing and filtering, probe data analysis and comparison, creating surface DB map contours, and generating filtered transient flow contours. So these are some of the key capabilities. Let's look at a few of them. So once the user has to read in the results coming out from CFD, so these are the flow results. And once these results are available in the time domain, the user can look at like basically do a probe analysis, so where he will select a particular element, or he can select particular coordinates, or he can do manual selection from the graphics area, and see the results in time domain, or he can see the results in frequency domain. The output type can be PSD or RSD. He can apply different scalings, like convert into different DBA contours, and also convert into results into narrowband or broadband in terms of octaves. And there are different signal processing parameters also available for this time domain conversion to frequency domain conversion. So this slide just shows the probe data analysis for one of the probes, how the results are looking in the frequency domain till 10,000 hertz in the narrowband. This is now this was for probe, so you see like there is one option for probe. The second option is for surface. So it is used to evaluate the results or the flow over the surfaces, and generate the DB maps, and it can also generate the filtered flow file using advanced signal processing. So for example, you can say like for what duration you want to see these results, or for what frequency range. Just a quick video showing the implementation. The user has to read the result files coming from UltraFluidX here, and once the results are loaded in, the there are two options. I'm currently in the probe tab, so user can select the element ID and he can choose whether he wants to view the results in frequency domain or time domain. So currently the option is chosen is frequency domain, and we can see the results in these are the results in frequency domain for narrowband. The user can change the response type here and see the results in time domain here. And now the users can go do broadband analysis. So here the results are shown in the octave band. In the surface tab, the user can select the result file and he can see the surface map for the different octaves. So very, very powerful feature to process the results coming from UltraFluidX. So this is a brand new feature and you can try and test it out in upcoming 2022 release. So I'm sure this is going to be very interesting for all the aeroacoustic, all the analysts or engineers working in the aeroacoustic field. So the next topic, and a very interesting topic, is on the seam. So I will pass on the presenter status to my colleague Uma Mahesh, who can take over this part of seam introduction.
Hello everyone, this is Uma Mahesh. Before I introduce you to this new SEAM interface, I just want to take over you to you what is SEAM, what kind of solver it uses, what are the benefits, and the comparison of the solver against FE to get to you an idea what exactly we are working on. So I'll just go through the presentation now. So Altair Scene is a software, is a structure standard solver for doing dynamic response analysis for both mid and high frequency analysis. It uses a statistical energy analysis software behind the scenes to solve the problem. The entities required for it are very different from FE. So the solving time is very good, and it runs the whole vehicle can run in less than 10 minutes if you take automotive, maybe even less than that. And Altair Seam was first to develop mid-frequency hybrid software, and it has capabilities of transient analysis also. And it maybe you are aware of it, but just to say, this Seam was acquired by Altair from Cambridge Solutions. So as I explained, SEAM uses statistical energy analysis software solver behind the screens, in which rather than finite element method, we use energy method to solve the equations. From the energy, we derive the displacements or pressures which are required for dynamic analysis, rather than FE, where we solve for displacements and then get energy and stress and strain. So here it is kind of reverse, and it uses statistical approach to do it. And the reason further I'll explain. So that is the main solver behind the screens, and it because of this statistical energy analysis, as it doesn't need any nodal information and it needs energy information, it can be used till high frequencies also. And it has a capability to solve both airborne and structure-borne analysis. Just a few brief benefits of SEAM. With SEAM, we are able to complete the whole suite of solvers, which help us from solving from low frequency to high frequency, ranging from 0 Hertz to 10,000 Hertz or 20,000 Hertz. So SEAM complements OptiStructs in a place where FE doesn't work fully because of computational requirements. And it has vast applications. It ranges from shipping industry, submarines, automotive, launching vehicles, helicopters, aerospace, enclosures, industry applications. So the applications for vibroacoustics at high frequencies all can be solved using SEAM. And the kind of software SEA, it's kind of monopolized market, so high business potential with SEAM. So just to briefly explain the difference between FEA and SEA. If you want to solve a vibroacoustic analysis of a small dash, for example, you need a minimum of 10,000 elements if you want to solve till 4,000 hertz to represent the dash. And you need acoustic elements of minimum of 30,000 elements to represent this. But when it goes to boundary element method or statistical analysis, the elements reduces drastically, but in SEA it even reduces drastically. The reason being we solve for energy of a subsystem rather than nodes, nodal displacements. So in similarly, the acoustic domains can be split into just 3 subsystems. The load casing is done in pre-processing as together, and same here it is done in SEA. In FEA, the majorly the connections apart from maybe major connections, node element to element connections is done automatically. But in SEAM, we need to define those connections between each subsystem. And the solver used is FEA solver, and we use SEA solver. And if you see the frequency range for 400 hertz, we need 30 minutes. And similarly, in BM, we need to solve till 400 hertz, we need 2 hours. Whereas in SEA, we need just less than 10 minutes to solve till 10,000 hertz. A small example of dash, how it looks in FE model, in FE world, and in SEAM world. So the same dash, when if you want to represent in SEAM or SEA model, the elements required or the subsystems required are very less. Because there is one more reason why it is like that is in low frequencies where FE works majorly, the deterministic peaks are very independent and they are very not coarsely placed. But as the frequency increases, the each peak comes together and it is very difficult to identify which peak is contributing. On top of it, you have manufacturing changes and even small changes at higher frequencies will have a change in mode effects. So you, whereas low frequency FE solvers are very good in helping you solve a particular peak using different diagnostic methods. But in high frequencies, that is not possible because they are very closely placed together. So this is the reason why mostly people use SEA solver, which is SEAM in our case, for solving high frequency problems. So this is the major introduction. Coming to SEAM strengths, basically it has a capability to solve both high frequency structure-borne analysis as well as airborne noise transmissions. And the SEAM solver doesn't require any, the requirements are very minimal. Even in a desktop of 8 to 10 GB, 8 to 16 GB, you'll be able to solve SEAM problems easily, even for a full vehicle level. And SEAM has a very great capability of incorporating the measured data of high frequencies like input load, structural damping, and acoustic absorption and modal parameters. So these are the major strengths. Maybe just to show you, this is the current SEAM before migration. Even though the solver was strong, the interface was very old and the usability was very bad. So the first step as a migration, what we did is we migrated the whole SE infrastructure into Unity, and this is the new interface. Whereas if you see here, that most of the displacement is done using representing network diagram, but now you have a 3D representation from which the user can the software can automatically calculate the SEA parameters which are required, like area, volume, connection areas, everything automatically. This way, this was a huge bottleneck for SEAM interface, where user was supposed to define each subsystem manually. He has to calculate it using geometry or FE and update it. But whereas here, we can simply build a model, or through the SE or using FE, we can convert it into SEA easily, and then automatically it captures all the required entities. So to do this interface, we have integrated this in Altair HyperWorks NVH, under which we have a separate profile called high frequency NVH to use this SEAM software. And we have dedicatedly built 2 ribbons for model building and analysis with various features integrated into each of these ribbons, ranging from SEA building the model, building the connections, noise control treatments or sound package, and setting up the property and material properties of the subsystems and connect and NCT layers. And once you have built the model using subsystems and connections, we can use the excitations available and we can run it and solve it. So mm, we have established new SEA entity workflows for each of them. So for structural subsystems, for acoustic subsystems, noise control treatments, connections and excitations, for each of them, we have developed a new workflows which are close to Unity workflow. So it is as good as working in Unity, and there is no difference. So now most of the workflows are integrated well into the Unity framework. So once we have this Unity framework, the next step, major step was, because the solving time was so low, it became important for us to have an integrated pre and post environment where you need to have able to see the results instantaneously and dynamically, because the solving time is very low. So we have given an option to right click on a subsystem and see the results. As well as we have a dedicated plot manager to the results, to see the results of all subsystems together. So this is integrated inside the same pre and post in a pre environment. So user doesn't need to shuffle between different environments. So another important thing was, as SEA is majorly based on areas, connections, and volumes, it became important for us that we use the available features like morphing, which will help us to quickly change the SEA subsystem parameters and improve. Let's say you want to see a design change, how if you increase the height of your vehicle by 90 mm or 100 mm, what is the effect of on the acoustic performance? So we can quickly do it. We can quickly update the theme model with the updated morphed subsystem entities, and we can see the results instantaneously. So in this way, we have used available morphing feature and integrated it in tightly into the process so that it becomes a singular environment. And high frequency NVH is currently under environment variable, and please contact us if you want to further try it out.